The moment of a force is to measure its tendency to rotate an object about some point. In the next session, we will discuss later how the physical significance of a moment is determined. To begin, we must understand the introduction of a moment by knowing its history. Archimedes was a Greek scientist, mathematician, engineer, inventor, and astronomer. Despite the fact that this is known about his life, it is recognized as one of classical antiquity's top scientists. Archimedes is considered as the greatest mathematician of ancient history and one of the greatest of all time foreshadowed modern calculus and analysis by using infinitesimal notions and the process of assumption to deduce and rigorously verify a variety of geometrical truths. His other mathematical accomplishments include obtaining an exact estimate of pi, identifying and exploring the spiral that now bears his name, and developing a technique for expressing very big numbers via exponentation. He was also one of the first to apply mathematics to physical phenomena, developing hydrostatic and static, as well as explaining the lever concept. He also was credited with designing innovative machines such as compound pulleys. Moments are scalar quantities that are used for hundreds of years in statistics for describing and characterizing their function, as well as in classical rigid body mechanics to measure the mass distribution of a body. They are also widely employed in statistics to explain the shape of probability density functions. The principle of moment is immediate from Archimedes' discovery of the lever's operating principle. He created physical modeling as well as the mathematics required to do so. Within the lever, a force, most typically a human muscle, is applied to an arm or a beam of some kind. Archimedes stated that the quantity of force applied to the object, the moment of force, is defined as m equal to ft, where F is the applied force and D is the distance between the applied force and the object. In contrast, the historical development of the term moment and its use in different branches of science, such as mathematics, physics, and engineering, is unclear. In 1565, Federico Comandino translated Archimedes into Latin as follows: a solid figure center of gravity is the point on which all its parts have an equal moment on all sides. In this context, the word moment in Latin, momentorum, is used in the way we understand it now as a moment about a center of rotation. The term moment was initially employed in mechanics to imply importance or consequence, and the moment of a force about an axis mean the importance of force in terms of its capacity to induce in matter rotation about the axis. However, the term moment has also come to be employed in a strictly technical meaning by analogy. This is evident in statements like a moment of a mass about an axis, moment of an area concerning a plane, both of which need definition. In some cases, there isn't necessarily a physical concept to go along with it, and such statements stand on their own both historically and scientifically by A.M. Worthington, 1920.
Hello, I am Perlin Cheng, and today I will be presenting my part, which is the background of case study. For case 1, this is a storyline. Harish has made a babysitting deal with his best friend. He is required to take care of his son, Daniel. Both of them come to agreement to bring the child to a playground. When bringing Daniel out, he is visibly bored. As an empath, he decided to use his engineering knowledge to impress Daniel. He told him that using a magic spell, he is able to weigh the same as him and can prove it using the seesaw at the park. Here is the question. In order to trick Daniel, Harish has to place himself at a certain length from the pivot of the seesaw in order to reach an equilibrium. Daniel weighs 45 kg and is sitting at a distance of 2 meters away from the pivot, while Harish weighs 75 kg. How far or close away from the pivot does he have to sit in order to reach moment equilibrium on the seesaw? This is case 2. Here's the storyline. Siti is a successful mechanic and has opened her own shop as soon as she graduated from university. Every day she focuses on maintaining and repairing cars and motorcycles. When it comes to changing tires, it's so easy she can do it in the blink of an eye. And here is the question. Siti always tightens the wheel nuts to 120 Newton meter. With a wrench at an angle of 32 degrees, measuring 420 millimeters, how much force should be exerted for the wheel nut to be tightened up to her standards?
When a force is applied to a body, it has a tendency to rotate about a point that is not on the force's line of action. This rotational inclination is occasionally referred to as a torque, although it is more commonly referred to as the moment of a force or simply the moment. The SI unit for torque are Newton meters. The force vectors may always be found on a plane parallel to the axis, regardless of its orientation in space. In order for a moment to exist, the force must operate on the body in such a way that it begins to twist. This happens if a force that is applied does not pass through the body centroid. A moment occurs when a force does not have an equal and opposing force acting in the same direction. For instance, we can take two examples that happen in our daily life where the first one is a wrench where we use to unscrew the bolt just like in figure 1.1. When a force F is exerted to the handle of the wrench, it tends to turn the bolt about the point of O. The moment's magnitude is proportional to the magnitude of F and the perpendicular distance or moment arm T. The larger the moment or turning effect, the larger the force or the longer the moment arm. If the force that is applied are not at angle of 90 degrees, it will be more difficult to turn the bolt since the moment arm will be smaller than the D, just like in figure 1.2. If the force is applied at 90 degrees or along the wrench, the moment will be zero because of the intersect point of O met the line of F. Hence, no turning can occur. Following with the second example is considering two persons on opposite sides of a door pushing on the door knob. There is a condition of equilibrium when both of them are pushing with equal force. If one of them suddenly jumps back from the door, the other's push would no longer have met with resistance and the door would swing open. A moment was made by the individual who was still pushing on the door, just like in figure 1.2. The element of the moment is defined as the product of the force and the moment arm T. The exact point at which the force causes rotation might be the center of moment. It might also be a reference point or axis around which the force is thought to be rotating. It barely matters as long as a specific point is used as the reference point at all times. The right-hand rule is used to sense the direction of the moment. The natural curl of the right hand's fingers as they are drawn towards the palm according to this rule shows the inclination of rotation generated by the moment. A clockwise rotation about the center of moment will be considered a positive moment, while a counterclockwise rotation about the center of moment will be considered as negative.
Bismillahirrahmanirrahim. So now I will continue the calculation to solve this problem. From the background study, we can obtain the information for us to solve this problem. And in case 1, we can see that Daniel's weight at 45 kg and the distance from the pivot is 2 meters. And Harish weighs around 75 kg and we need to calculate the distance from him from the pivot so that he can counter the weight of Daniel. So the step for the solution is first we need to find the moment for Daniel in clockwise direction. So we need to use his weight multiplied by the constants for gravity and multiply it with the distance from the pivot, and we will get the moment is 882 and 9 Newton meter. And from that value we can find the moment for Harish using the formula m equals Fd, and then we can enter it into the equation to find the distance for Harish. So Harish has to sit 1.2 meters away from the pivot to balance the weight of Daniel so that they are in equilibrium. In case 2, the moment required for tightening the nut is 120 Newton meter, and the distance of the bolt tightener is 420 millimeter, which is equals to 0.42 meters. So using the formula m equals Fd, we can see that the force required to tighten the nut is 285 and 71.71 Newton. And in order for us to find the required force to tighten the nut, we will use the formula of F sin theta, and we can see that the upward force to tighten the nut is 151.40 Newton.
So I'm going to brief about the discussion. So the discussion said, based on the topic given to us, which is moment, we have found certain application of moment in real life. With reference to the theory of moment, the net moment about one axis on an object is equal to the total of individual moments acting along that axis. If multiple forces is applied and no rotation is seen, the moment is equal to 0. For the first case, the seesaw is the perfect example of multiple forces acting on one axis. One on the left, which is Daniel, and the other one is on the right, which is Harish. In order to find the distance of where Harish should sit to balance the seesaw from the pivot, we must know that the sum of moment is equal to 0, like I mentioned before. By using the formula m equal to Fd, which is F is force equal to mass times 9.81, which is the gravity, and d is distance from the pivot. By sum up all the moments and equal them to 0, we got that the distance of where Harish should sit is 1.2 meter from pivot in order to balance the seesaw. Let's move to the second case. Here we can see only one force is applied on one axis, which is the wrench. Using the same formula of moment m equal to Fd to find the force needed to tighten the nut, first of all, the moment has been given. Insert the value to the formula and easily we can get the force that should act on the wrench. However, it's not easily as we thought. The force is perpendicular to the wrench and we must find the force of y-axis, which is the hand. We can use the angle given to find the force on the y-axis, which is the force applied by CT to tighten the nut. So conclusively, from all the calculation and analysis that has been made, we can state that the theory of moment is proven. Therefore, moment is crucial and often used on daily basis. It is important for us to learn this one.
Congratulations! You reached the conclusion. So, a moment of force is a measure of a tendency of a force to rotate a body on a point. So, to develop that moment, the force must act upon the body to attempt to rotate it. So, in order for a moment to develop, the force must act upon the body in a way that the body has to twist. So this occurs every time a force is applied, so it doesn't pass through the centroid of the body. A few key scenarios that are present when we have to deal with moments in question are when the total moment is 0, it's considered to be equilibrium. Number 2, two equal forces of opposite direction with a distance between them will cause a special case called a couple moment. Number geometry, the principle of moments, or Vergnon's theorem, states that the moment of a force about a point is equal to the sum of the moments of the force components about the point. So this helps when figuring out a moment when not all the information is known in the problem. Moment is a very useful concept in real life because it helps in determining the direction, magnitude, and angle of the object that is being rotated. And due to the discovery of this concept, it was applied in multiple scenarios that can be found in everyday life if you look around. So a few examples could be seesaws, hinge doors, wrenches, or even steering wheels. So yeah, that ends our presentation. Thank you so much for listening.